All right, welcome to your very first day here at Durga Analytics. I'm going to be your technical instructor, and I'll be guiding you through this entire front office quant whiteboard masterclass. Over our time together, we're going to transform you into a highly capable quantitative analyst. And not just any quant, but one specifically engineered for the high-stakes, hyper-complex world of gas and power trading. So grab a coffee, get settled, and let's dive right in.
Before we even think about writing a single line of Python, let's take a quick look at the 100-chapter roadmap we're going to conquer together. We've got 12 modules in total. We kick things off with Module 1, Front Office Quant Foundations. From there, we build up, moving through commodity markets, mathematical foundations, forward curve construction, core pricing, advanced structures, risk management, quant libraries, front office programming, working with sales, model risk, and finally, we wrap it all up with 4 capstone desk projects. It's a massive journey, but we'll take it step by step.
So, dropping a pin right exactly where we are today in Chapter 1, we are laying the absolute bedrock. We're going to cover what a quant actually does on a day-to-day basis, how we measure price and risk, the core math of expected value, and we'll even tackle your very first Python implementation. No prerequisites, no installed software to worry about just yet. It's just you, me, and the core logic.
Okay, Section 1. Why it matters and the front office quant role.
Let's start with the immediate business problem that actually justifies your seat on the trading floor. Picture this scenario. A trader comes to you. They have exactly 10 minutes to price a 50 million pound gas contract. Should they do the deal? At what price? Think about the stakes here. If your pricing model is off by literally just 1%, the desk loses £500,000 in an instant, right? Who decides what the right price is, and how do they know it's actually right? Well, you are the person who ensures that massive loss does not happen. And that brilliantly illustrates our one-line definition of the role. A front office quant turns a trader's intent into a trustworthy number, a number you can defend, using math and code. To make sure we're on the same page for the next 99 chapters, let's rigidly define a few core terms. A quant builds a simplified model to estimate price, which is essentially just fair value today. At the same time, we calculate the risk. What happens if the market moves against our expected payoff? And payoff is simply the money you receive at the very end of a contract. Moving on to Section 2, the desk ecosystem and quant outputs. We really need to map out exactly where you physically and operationally sit within the bank. Because, front office isn't just a corporate buzzword. It's a very specific, high-pressure environment. You're not tucked away in some quiet back office writing academic papers. You sit right alongside sales and traders. You are peers. Information flows back and forth instantly. A trader asks you a question, you answer, they push back. It's highly collaborative. And it's only after a trade is actually executed that the data flows downstream to the middle office for risk management and then to the back office for operations.
If we strip away all that high-level jargon, your entire job really just boils down to producing 3 specific things, instantly and repeatedly. First up, a fair value price, meaning how much is this specific deal worth today? Second, risk. If the market shifts, what exactly happens to my position? We often refer to this sensitivity as delta. And third, the tools. The actual underlying Python code that recalibrates that price and risk in milliseconds the moment the market moves.
All right, Section 3. Why gas and power specifically?
Now you could easily be a quant for equities, currencies, or bonds. So why focus entirely on gas and power? Well, mostly because energy absolutely breaks standard financial models, and knowing how to rebuild them is a highly, highly lucrative skill. Think about the calm, gentle, non-seasonal movements of a standard equity share. A share you buy today is the exact same share next year. Now contrast that with power prices. Power is violently spiky. It's heavily seasonal. It might drop in the middle of the year and then explode with massive price spikes. Why? Because electricity literally has to be consumed the exact millisecond it's generated.
These physical realities create some pretty severe domain constraints. Like we said, electricity cannot be stored in a warehouse. Its price is incredibly dependent on the weather. Pricing it requires optimizing intense physical constraints, like pipeline limits, or how fast you can inject gas into a storage cavern. And it involves these weird custom agreements. A great example is the swing contract, where a buyer can actually vary how much gas they take each day. Pricing that complex swing contract, that is exactly what we're going to build from scratch in Project 1.
Okay, Section 4, Mathematical Foundation, specifically expected value.
Let's transition from the business problem into the math. We're going to do a quick, simple intuition exercise to compute our very first fair value completely by hand. Imagine you have a contract that pays out the value of 1 apple tomorrow. Step 1 is listing all the possible outcomes. Let's say the apple is worth 2 pounds if it's sunny or 0 pounds if it's rainy. Step 2 is computing the probability weighted average. For the sake of this example, let's assume sunny and rainy are equally likely, a 50% chance for each. So what is a fair price to pay for this exact contract today?
If we visualize this, branching out from today, we get a probability tree. This is essentially our pricing engine in a single picture. We assign a 50% probability to a 2-pound sunny day and a 50% probability to a 0-pound rainy day. All we are doing is simply multiplying each outcome by its probability and adding them up to find the average across all possible futures.
Now, in formal quant finance, we write this out with a stylized E, followed by square brackets containing the word payoff. That E stands for expected value, and the square brackets hold exactly what we're averaging, in this case, the contract's payoff. The absolutely crucial takeaway here is that expected value is just a weighted average. It is not a crystal ball prediction of the exact future. Executing that basic arithmetic, 2 pounds times 0.5 gives us 1 pound, plus 0 pounds times 0.5, which is 0. So our expected value, and therefore our fair price today, is exactly 1 pound. Think about it. If someone offers to sell this contract to you for 80 pence, you buy it immediately. If they ask for £1.20, you walk away. And the machinery works exactly the same no matter the odds. If the chance of a sunny day was 75%, you just run the same math and the value would be £1.50.
That brings us to Section 5, Python Implementation and Course Projects.
Let's see how this whiteboard math translates into the engineering architecture you'll actually use in production on the desk. Translating this to Python is incredibly straightforward. We simply assign our probabilities and payoffs to variables. For instance, prob_sunny equals 0.5, payoff if sunny equals 2.00. Then we just write out the formula for expected value using those variables. Variables, by the way, are really just named boxes in the computer's memory. The real magic here isn't the math itself. It's the fact that a computer can mechanically execute these arithmetic steps millions of times without ever breaking a sweat.
So you might be asking, why use Python at all if the math is just basic arithmetic? Well, a computer is an absolute necessity because a real energy contract, like that gas swing pricing engine we build in Project 1, doesn't just have 2 outcomes. It involves millions of possible futures across hundreds of delivery days. A human obviously can't sit there and average millions of branches by hand. But code? Code can process that massive probability tree in a matter of milliseconds.
All right, final section for today, common pitfalls and the career path. To wrap up this engineering design review, let's talk about where junior developers typically trip up on the trading desk. First, never, ever confuse your expected value with the actual future payout. Our Apple contract pays exactly 2 pounds or 0 pounds. It literally never pays 1 pound. The 1 pound is just the pricing average. Second, do not trick yourself into thinking you are predicting the future. You aren't. We are simply pricing risk based on the information we have today. And third, never forget that a model is just a deliberate, useful simplification of reality. If you go in assuming energy works identically to equities, you are going to lose the desk a very, very large amount of money.
Now, the upside. Mastering this domain is incredibly lucrative. A graduate quant in the UK can command anywhere from 70 to 100K right out of the gate, scaling up to 200K plus for senior roles. In places like Singapore, seniors at global funds can easily see compensation upwards of 500,000 SGD. The market pays a massive premium for the rare intersection of fluent Python skills, solid probability intuition, and deep, specialized knowledge of energy market nuances.
And hey, if you're ever sitting in an interview and they hit you with the classic question, explain expected value to a non-expert, well, you now have the exact methodology to ace it. You just walk them through the fruit-style apple contract, you list the outcomes, you weight them by probability, and you average them out. It's that simple.
Because ultimately, every single sophisticated model we are going to build over the course of this 100-chapter masterclass is really just attempting to answer one fundamental question: what is this uncertain future worth today? I want you to keep that provocative thought in mind as we move forward. In Chapter 2, we are going to zoom out and explore the entire trading desk ecosystem to see exactly who is relying on your answers. All right, that's it for today's explainer. I'll see you in the next session.
All right, welcome to this explainer. I'm your instructor from Durga Analytics, and today we're tearing down the commodities trading desk. But look, we aren't going to just stare at a boring corporate org chart. Instead, I want you to look at the desk ecosystem as a hardcore, rigorous engineering system. In my experience on the trading floor, treating the flow of a trade like data moving through a highly optimized software pipeline with strict latency requirements and independent control gates is absolutely non-negotiable. If you're a quantitative analyst, a developer, or a software engineer stepping onto a trading floor, understanding this system architecture is the single most critical prerequisite to your success.
Now, before we map out the actors in this system, let's quickly anchor ourselves. This explainer is pulled straight from our front office quant commodities curriculum at Durga Analytics. It's a massive, cumulative journey. We're talking 12 modules and 100 chapters total. It takes you from the absolute basics through advanced gas and power structures right into complex system architecture and capstone desk projects. Right now, we're diving into Module 1, Chapter 2, the trading desk ecosystem. This is a foundational piece, but trust me, it feeds directly into the real-world applications we're going to build later, especially Capstone Project 4, the Trader Risk Dashboard.
Here's our roadmap for this chapter. First, quant foundations. Then, the desk ecosystem teams, the journey of a single trade, modeling desk data and projects, some common mistakes, and a self-check. And we'll wrap it up with a recap and next chapter.
As you can see, our sequence builds super logically here. We're not just throwing code or math at you right out of the gate. We start with why it matters and the big picture. From there, we build up the components, trace the information flow, translate that whole thing into Python, connect it to our capstone project, and recap. It's a full pipeline designed to show you exactly where you, the quant, fit into this massive machine. All right, Section 1. Quant Foundations, and Chapter 2. Let's look at the actual business problem here.
Picture this. It's 9:14 a.m. The market is absolutely ripping. A salesperson leans over your desk and shouts, "Client needs a price on 100,000 units of January gas. They are on the phone right now." The trader immediately spins around and looks at you, the quant. You've got 90 seconds. 3 people are waiting on one single number from your model. If you miss your cue, the client hangs up and the deal is dead. But if you deliver the right number instantly, the desk just won a massive piece of business. That right there is why we are studying this ecosystem. You could build the most mathematically beautiful, technically flawless model in the world, but if you don't know exactly who is consuming it, what format they need, and how fast they need it, well, your model is practically useless. Okay, moving on to Section 2. The desk ecosystem teams.
To actually deliver that crucial number, we've got to map out the actors in our system. Think of it kind of like tracking an order flowing through a Michelin-star restaurant kitchen. The desk operates on a strict architecture with a very clear separation of concerns. At the top, You've got clients generating the demand. Below them, there's a hard split between the front office, where the risk is taken, and the middle and back offices, which act as independent control gates and processing units. Let's break these nodes down.
First up, the front office. These are your market-facing teams that are actively taking on risk. We're talking sales who talk directly to the clients and traders who actually decide the quote and own the resulting P&L. And crucially, it includes you. As a quant, you sit horizontally right next to the trader as a peer in the front office. You're the one feeding them the fair values, the pricing algorithms, and the real-time risk measures they absolutely need to survive. You're a primary driver of the revenue generation.
Now, directly below the front office, we have the middle and back office. The middle office is risk management. Think of them as your independent validation pipeline. They are constantly checking that the front office isn't taking on more risk than the bank actually allows. They monitor the limits. Then there's the back office, which is operations. Operations make sure the physical and financial settlement actually happens. They schedule the gas or power delivery and settle the cash. They're the final execution layer, turning a paper trade into physical reality.
Which brings us to Section 3, Journey of a Single Trade.
With our core components mapped, let's trace the precise flow of information for one single deal across this architecture. Every single interaction arrow you see here is absolutely critical. We might not have the heavy math just yet, but this data flow is the literal foundation of your software design. Every step from 1 to 6 is a state change in the trade lifecycle, and each one is a potential integration point for your tools. Let's walk it through.
Step 1. The utility client tells sales they want to fix their January gas price. Step 2. Sales relays this to the trader. Step 3. And hey, this is where your code executes. The trader asks you, what's January gas worth and what's my risk if I sell it? You immediately return a fair value and a risk metric. Step 4. The trader tacks on their margin, quotes the client, and boom, the client agrees. The trade is struck. Step 5. Instantly, risk management checks if this new position breaches the desk's limits. And finally, Step 6. Overnight, operations confirms the trade and schedules the settlement. One phone call, 5 different roles, touching the trade exactly once in a perfect optimized sequence.
Let's jump to Section 4, Modeling Desk Data and Projects. Let's talk about the strict timeline of a deal, because quants don't just see people at desks, we see programmable data and project specs. The client calls at 9:05 a.m. The deal is agreed upon by 9:12 a.m. Do the math. You had roughly 7 minutes for your pricing models to run, for the trader to parse the output, and to negotiate the whole deal. This timeline directly informs Capstone Project 4, your trader risk dashboard. Your dashboard absolutely cannot be some slow, clunky batch process. It has to instantly serve pricing to the trader and instantly update risk metrics for the middle office the literal millisecond the trade is struck at 9:12 a.m. The system architecture is your software requirements document.
And the cool part? We can start building this right now. Even without advanced stochastic calculus, we can start translating this real-world structure into Python using core data structures. How? By using dictionaries to map the entities, pairing team names with their exact responsibilities, and we use loops to iterate through the sequential journey of the trade. We're literally taking the physical desk and modeling it as abstract data. Later in the course, you're going to use these exact same concepts to model complex forward curves and exotic derivative structures.
All right, Section 5, Common Mistakes and Self-Check.
Just like any rigorous engineering review, we need to look at the system's failure modes. What happens when this pipeline breaks down? Well, I've seen these traps firsthand on the trading floor. Mistake number 1, building for yourself instead of the trader. Delivering a technically correct number in a format that can't quickly read on a chaotic phone call, the value is 0. Second, forgetting that risk management is an independent control gate. They aren't an obstacle to work around, they're a structural necessity keeping the bank solvent. Third, ignoring operations. If your pricing tool spits out a complex structured trade that the back office literally cannot schedule for physical delivery, congratulations, your profitable trade just became a massive real-world loss. Finally, the maximum precision fallacy. Handing over a perfectly precise number 10 minutes late is totally useless if the trader needed a mathematically good enough number in 90 seconds. On the front lines, latency often beats ultimate precision.
Let's hit pause for a rapid-fire self-check to make sure we've really internalized this architecture. Think about the system design for a second. Why do we deliberately architect the middle office, risk management, to be completely structurally independent from the front office? Why not just have the traders check their own risk and save everyone some time?
Well, the answer comes down to pure system integrity. The people controlling the risk simply cannot be the same people taking the risk and earning their bonuses based on those profits. It's the oldest rule in the book: nobody marks their own homework. This structural independence guarantees that the risk checks remain completely honest and objective, ensuring that trading limits are strictly enforced to protect the entire firm from a catastrophic blowup.
And that brings us to Section 6, Recap and Next Chapter.
Before we move to the next module, I want you to burn this fundamental engineering principle into your brain as you progress as a front office quant. Technical perfection is completely useless if it doesn't serve the specific real-world needs of the sales, trading, risk, and operations teams. A model is only as valuable as the desk's ability to actually use it in the heat of the market. Knowing exactly who sits where and what specific data they require is step one to building tools that people will actually rely on.
So, we've nailed down the static architecture of the desk. In our next explainer covering Chapter 3, we're going to put this entire ecosystem on a clock and look at a day in the life of a gas and power desk. But before we wrap up today, I want to leave you with a thought. If a massive market shock hits tomorrow and prices gap 20% in 3 seconds, is your Python code robust enough and fast enough to keep your trader alive? Think about that system latency, and I'll see you in Chapter 3.
Welcome back to the Durga Analytics Front Office Quant series. Today, we're diving deep into Chapter 3, which is an explainer all about a day in the life of a gas and power desk. You know, if you really want to build systems for traders, you first have to understand the incredibly intense, clock-driven environment they actually operate in. Just as a quick refresher on our overarching 100-chapter curriculum, we are currently right here in Module 1, Chapter 3. We're building the absolute groundwork right now before we hit the heavy quantitative modeling in Modules 3, 4, and 5. Because frankly, you have to know the ecosystem before you can write the algorithms that power it. So this diagram is basically our blueprint for today's engineering review. We'll move sequentially from the core business problem, meaning why any of this actually matters, straight through the big picture, the math, the Python requirements, and finally to how this impacts your capstone projects. Every quantitative model you're going to build in this course is heavily influenced by this exact workflow progression.
Here's our agenda for Chapter 3. We're covering desk terminology, the 0658 cold snap, the morning dependency chain, the 3 trading phases, engineering trade-offs, and desk projects and pitfalls. Let's jump in.
Section 1. Desk terminology. Right, before we put our desk on a live clock, we absolutely must establish the core outputs your Python systems will be generating. First up is mark-to-market, commonly called MTM. When traders ask you for the mark-to-market, they're simply asking your quant tools to revalue their current positions based on the absolute latest prices to determine profit or loss. Think of it like this. If a trader bought gas yesterday at £40 and today the market says it's worth £42, well, your MTM calculation needs to instantly reflect that £2 profit across their entire portfolio.
Similarly, we have the curve mark. This is the mandatory process of updating the forward price curve so that every pricing model has fresh, accurate data inputs. The forward curve is effectively a timeline of future prices. Your system needs to pull in the latest market data and literally mark or update this curve. Without a fresh curve, I guarantee you, every single downstream valuation is effectively garbage.
Section 2, the 0658 cold snap.
Let's plunge straight into the real-world stakes of front office engineering. I want you to imagine this exact scenario. It's 0658 in the morning, 2 minutes before the desk officially wakes up. Overnight, while the traders were fast asleep, a cold snap hit Northern Europe and gas prices just violently jumped 4%. Every single price on the desk screens is now completely stale. In the next hour, before a single client even calls, your automated tools must rebuild the entire pricing picture from scratch. If they don't, the desk is trading blind. In this business, speed is absolutely just as critical as the mathematics.
Section 3, morning dependency chain.
Now, to successfully rebuild that overnight picture, your automated systems have to respect a strict, non-negotiable engineering order. This is your core data flow architecture, and it is strictly linear. Market data from exchanges like ICE or EEX is ingested first. That raw data is required to build the forward curve. Only once you have a curve can you feed your pricing models. Once positions are priced, then you can compute risk metrics. And finally, that all culminates in P&L. You cannot price without a curve, and you cannot build a curve without data. If you break this chain anywhere, say your market data feed goes down, absolutely nothing downstream can be trusted. Every model we build in this curriculum sits somewhere on this exact chain.
Section 4, the 3 trading phases.
Let's map out how this pipeline actually behaves chronologically. A trading day is, well, it's effectively a theater performance, right? You have 3 distinct acts. First, there's the meticulous setup before the doors open in the pre-market around 7 a.m. Second is the live show of the trading session beginning around 9 a.m., where latency is absolutely critical as traders buy, sell, and hedge. And finally, you have the tidy-up phase during the end-of-day close around 17 p.m., which is where the official marks are set. Notice how your workload as a developer beautifully visualizes this timeline. We see a massive computational spike in the morning. That's your systems working incredibly hard to ingest overnight data and rebuild those forward curves. Then it plateaus during the live session, where the system shifts to on-demand, low-latency pricing. And finally, the workload peaks again at the close to compute the heavy, highly accurate end-of-day risk calculations. Your software literally has to dynamically handle these drastically varying load profiles.
Section 5, engineering trade-offs. Because the environment changes so much throughout the day, your Python systems must dynamically adjust their optimization priorities. Reading across this matrix, there's a very clear engineering trade-off. During the pre-market, we need a fresh forward curve. The speed requirement? Minutes. We prioritize data completeness over raw speed. But look at the live session. We need fair deal values and position risk. The speed requirement here is seconds, honestly sometimes milliseconds. When a client's on the phone, sub-second latency is absolutely demanded. Then, at the close for end-of-day P&L and risk, we shift back to minutes. Why? Because here, perfect accuracy is required, since these are the firm's official numbers. Knowing which regime you're in totally dictates how you design and optimize your code.
So when you actually go to implement this in Python later in the course, we aren't just going to talk about schedules abstractly. We'll represent this daily timeline as real tabular data. We start simple with lists of tuples, fixed little groups of related values like time and event. But very quickly, we're going to supercharge those into pandas data frames. Data frames allow for high-speed automated filtering, which lets your systems instantly query things like, what are the live prices right now? Or generate the EOD report, handling thousands of rows of schedule and price data completely seamlessly.
Section 6, desk projects and pitfalls.
Okay, so how does this daily rhythm impact the actual software you'll build in your capstones? Let's make the math commercial for a second. Imagine a 14 o'clock client call. The client asks for a price. Your complex, mathematically perfect model calculates the fair value as £42.40. Under option A, your system is fully optimized for the live session and returns this quote in 2 seconds. The trader confidently relays it, and boom, the trade is won. Under option B, your system produces the exact same perfectly correct £42.40, but it takes 90 seconds to compute because you forgot to cache the forward curve in memory. By the time that number pops up on the screen, the client has already hung up and gone to a competitor. Commercially speaking, a right answer delivered late is just a wrong answer.
As you transition onto the desk, you really must avoid these common rookie pitfalls. The deadliest mistake is optimizing for exact to-the-penny accuracy at the expense of speed during live sessions. Like we just saw, delivering a perfect value after the client hangs up is worthless. Secondly, please do not treat the end-of-day close as a mere formality. Those numbers literally go to the regulator and the risk officers. Third, never assume yesterday's curve is valid today. Always account for the overnight gap. And finally, a trading desk is a chaotic place. Don't confuse reacting to constant interruptions with deep, productive software engineering. You have to protect blocks of your time to actually build the infrastructure.
Let's pause here and synthesize this with a quick self-check question, straight from the curriculum material. Think about the engineering trade-offs we just discussed. Why exactly do we accept slightly slower computational systems at 1700 during the close, as long as their output is perfectly accurate? Well, the answer is all about systemic trust. The close establishes the official marks that feed the entire firm's overarching P&L and risk profiles. These are the numbers the bank relies on overnight. Errors here are highly visible, they get reported to management, and worst of all, they become the starting picture for the following morning. The daily cycle is a loop, it's not a straight line. If you end the day with bad data, you start tomorrow with bad data. Therefore, accuracy vastly outweighs the need for sub-second latency at 1700. Every single automated tool we build in this course is ultimately designed to give traders back their time, to automate the morning refresh, to provide instant live session pricing, and to guarantee an incredibly accurate evening close. In our next explainer, Chapter 4, we'll leave the organizational chart behind and start writing code for the raw material itself, calculating prices and returns. How do we actually translate market data into the mathematical language of trading? Well, that is up next. Until then, ask yourself, if the cold snap hit your automated desk tomorrow morning, would your Python code win the trade, or would your client be left waiting on the line? Welcome back, everyone. I'm your technical instructor from Durga Analytics, and today we're putting Chapter 4 under the microscope. We are talking about prices, returns, and the language of markets. As experienced developers or aspiring front office quants, you need to know exactly how money moves before you start modeling it. So let's jump right into this foundational explainer. Just to contextualize exactly where we are, remember that our complete front office quant curriculum spans 100 chapters across 12 modules. We take you all the way from these basic foundations, right through advanced commodity derivatives, algorithmic curve construction, and all the way to our capstone desk projects. Today, we're firmly planted in Module 1, Chapter 4. We are laying down the absolute mathematical groundwork for everything that follows. Think of today as an engineering design review. We'll briefly look at the foundational course map, define our core market variables, break down the actual mathematics of profit, unpack the crucial difference between P&L and returns, and finally wrap up with system architecture and some unit tests. Okay, Section 1, the foundational course map, navigating the chapter workflow. Our learning path today essentially operates like a conceptual deployment pipeline. We're moving sequentially. We start with a raw business problem on a real trading desk, push through the core math and data types, move into the architectural logic for our later Python projects, and finally, we hit the recap. Let's move into Section 2, defining core market variables, translating desk reality into data types. Picture this business problem on a real gas and power desk. Two traders are staring at the exact same screen. watching the exact same gas price tick from 30 to 33 pounds per megawatt hour. One trader is grinning, the other is swearing. It's the exact same 3-pound move, yet they are experiencing entirely opposite fortunes. Why? Well, the only difference between their portfolios is a single minus sign. Today is entirely about mastering that sign and translating the reality of the desk into strict data types before we write a single line of Python code.
First things first, we have to draw a strict line in the sand between price and return. Imagine you're watching a single unit of gas. On Monday, it costs £50. On Tuesday, it's £52. The price change is £2, right? Price is an absolute state. It's a snapshot in time that tells you exactly where you are. Return, on the other hand, is a proportional change. £2 out of a £50 start is 4%. It tells you how far you traveled relative to where you began. Because returns are unit-free ratios, they let us compare vastly different assets on the exact same scale.
Next up is position. And please don't treat this as abstract financial jargon. I want you to treat position as a simple, explicit integer variable in your database that dictates your market exposure. If you hold 100 units, your position is simply positive 100. If you've sold units you don't actually own, it's negative 100. It's that simple.
Which naturally brings us to the term long. Being long just means your position carries a positive sign because you own the asset. Your profit aligns directly with an upward trajectory in price. Price goes up, you make money.
Conversely, we have short. Now, I know this concept can sometimes confuse newcomers, but on a trading desk, it is a completely routine, everyday transaction. Being short introduces a negative integer position. It means you sold something you don't currently own with a promise to deliver it later. You profit when the price falls because you can buy it back cheaper than you originally sold it for. That fundamental asymmetry is exactly why the position sign is negative.
And that brings us to this elegant, universal formula for profit and loss, or P&L. P&L simply equals your position multiplied by the new price minus the old price. The sign of your position integer, that plus or minus, does literally all the heavy lifting here. It mathematically determines if you made or lost money on any given market move.
Moving on to section 3, the mathematics of profit. Let's actually run these calculations.
Let's test our new vocabulary with some hard numbers, focusing on that exact same gas price move from £30 to £33 we talked about earlier. Just read the return formula aloud in your head, new minus old divided by old, right? So 33 minus 30 divided by 30. That gives us 3 over 30, which is exactly 10%. We get a clean 10% return, and notice how it's completely independent of position size. It perfectly converts this asset's performance into a universal, comparable percentage.
Now take a look at this chart. Look closely at the x-axis for price and the y-axis for P&L. Notice that perfect mathematical mirror image? It proves that at absolutely any price, the long position's exact gain is the short position's exact loss. They cross right in the dead center at the entry price of £33, where neither side has made or lost a penny. That flawless symmetry is driven entirely by that single minus sign in the position variable. All right, section 4, P&L, adds, returns, compound. This right here is the most critical bug you will see in performance reporting. Let's trace a long position of 100 units over 3 days to see exactly where software bugs creep in. Day 1, price goes from £30 to £33. P&L adds £300 and your return is positive 10%. Day 2, the price drops to £31.50. P&L drops by £150, making the return negative 4.55%. Day 3, price rises to £34.65. P&L adds £315, return is positive 10%. Now look at the totals row. The P&L elegantly adds up right down the column. 300 minus 150 plus 315 gives us exactly £465. Perfect. But the return? If you simply try to add 10 minus 4.55 plus 10, you'd get 15.55%, but that is mathematically wrong. The actual return is 15.5%. Why? Because each day's percentage applies to an already changed price. Returns absolutely must be compounded. They are multiplied across time. So 1.10 times 0.9545 times 1.10 minus 1 gives us the true 15.5%. Remember this ironclad rule for your systems. Pounds add, returns multiply. Let's look at Section 5, System Architecture and Pitfalls. How we integrate this with the broader quant stack. You might be wondering, how do these seemingly isolated formulas plug into the enterprise systems we'll be building in later modules? Well, they aren't just textbook equations, they are literal architectural components. Step 1, that simple P&L formula, position times new minus old, will literally be the engine driving the daily trader risk dashboard when we get to Project 4. It'll iterate and sum across the entire book of trades. Step 2, the returns calculation feeds directly into Module 3's volatility engines. We'll take those return ratios, extract them, and measure the spread of daily returns to calculate historical volatility, which then powers complex option pricing and our value at risk models. Now consider this slide your ultimate software quality assurance checklist. These are the most common code review mistakes you absolutely must avoid. Number 1, mixing up a raw price change like plus £2 with a proportional return like plus 4%. Number 2, losing the minus sign of a position. This is disastrous. It'll literally turn a massive short loss into a fake profit on a trader's screen. Number 3, assuming a short position is some exotic red flag rather than a routine daily transaction. And finally, as we just proved, adding returns across multiple days instead of compounding them. Any single one of these bugs will instantly invalidate your entire risk system. All right, Section 6, unit tests and next steps. Let's verify your mental model. Before we even think about moving to Python, let's run a few rapid-fire unit tests. Test number 1. Ask yourself, if you are short 200 megawatt hours sold at £20 and the price is now £25, what is your P&L? Well, the position is negative 200. The price rose by 5. What does our math dictate? Negative 200 times positive 5 equals minus £1,000. Because you were short, a rising price is the exact opposite of what you want. It forces you to eventually buy it back at a higher price. Test number 2. A price rises 10% on Monday and 10% on Tuesday. Is the 2-day return 20%? Think about it. If you answered yes, you just failed the code review. Remember, the second day's 10% applies to an already raised price, so 1.10 multiplied by 1.10 actually yields a 21% compounded return. Two 10% days strictly beat a flat 20% move. I'll leave you with a direct quote from the curriculum. Every P&L number on every desk in the world is at heart the formula you just learned. Master the sign, and you've mastered the scoreboard. Now that you deeply understand the raw physical laws of market math, are you ready to finally spin up your Python environment in Chapter 5 and bring these variables to life? I'll see you in the next chapter.
Welcome to this explainer on Chapter 5 of the Durga Analytics Front Office Quant course. I'm your host, and today we're actually going to hit pause on the complex math so we can focus on establishing a pristine, completely predictable Python environment. Look, this isn't just some boring IT checklist. It's a critical survival skill on a live trading desk. Whether you're a front office quant developer, an energy trader, or an engineer, your workbench absolutely has to be flawless.
Here's a quick look at our agenda for today. We'll cover why this matters, break down the Python lab architecture, install your workbench, get into the verify then trust habit, run your first script, and then tie it all back to our real-world projects.
Just to ground us in where we are, we're currently in Module 1, Chapter 5 of our massive 100-chapter curriculum. Before we move into gas and power markets,
forward curve construction, and all those advanced capstone projects later on, you need a reliable lab. I can't stress this enough. This chapter is the technical bedrock for the entire course. A quant who can't get a clean Python environment working is literally like a chef trying to cook without a kitchen. It just doesn't work.
Okay, Section 1. Let's talk about why this actually matters.
On a real trading desk, 10 minutes of careful setup right now is going to save you 10 hours of agonizing debugging later. Trust me on this. The most common reason a beginner stalls out in week 1 isn't the math. It's an environment that kinda almost works, but then spectacularly fails right in the middle of building a critical pricing engine. We're securing that foundation today.
To speak the language of the desk, we've got to precisely define our toolkit. Python is the programming language itself. The interpreter is the engine that actually runs your code line by line. Packages are just reusable blocks of code that other people wrote, like NumPy or Pandas. Now, a virtual environment is a completely isolated space. This is absolutely crucial on a desk so that updating a package for your pricing model doesn't accidentally break your risk dashboard. Pip is the installer you use to download those packages. And a script? That's just a saved .py file containing your code. That's the whole shebang.
Moving on to Section 2, the big picture of what a Python lab actually is.
Take a look at the workflow on the screen. Notice the arrows. You write, you run, and then you check. This is your daily reality on the desk. You've got an editor where you write your code and save a .py file. You have a terminal where you type your commands. And you have Python, which is the engine that actually reads and runs that code. So it's a constant loop. Write, run, verify. Now, the single biggest rookie trap I see is confusing the editor with the terminal. You have to remember, the editor just saves text to your hard drive. It's basically a smart word processor. It never actually runs anything. The terminal, on the other hand, is your command center. That's where you literally order the Python engine to execute that saved text.
Section 3. Building this up from zero and installing Python.
You've basically got two paths here. Option A is the official installer straight from python.org. If you're on a Windows machine, ticking the box that says Add Python to Path before you hit install is an absolute mandate. Seriously, if you skip that, your terminal will throw a command not found error because it has no idea where the Python engine lives. Option B is Anaconda. Quants absolutely love this one because heavy scientific libraries like NumPy are built in C, and compiling them from scratch is a huge headache. Anaconda comes with all those batteries included. Either choice is fine. Just make sure you secure the engine so we can run the rest of our modules.
All right, Section 4, the math. We're taking it very gently today, essentially no math. But we need to establish a habit that is well worth its own worked example.
Look, writing a script that prints "Hello World" is cute, but it proves absolutely nothing about computation. So we're going to use the Chapter 1 Apple contract to properly test our engine. Let's calculate the probability weighted average by hand real quick. There's a 50% chance of making $2 if it's sunny and a 50% chance of making 0 if it's rainy.
That gives us exactly 1 pound. We are establishing this 1 pound as our known expected fair value. Meaning, when our script eventually outputs this exact number, we haven't just proven that Python can print text. We've verified that our Python lab can mathematically compute. We make a prediction and we demand that the machine matches it.
Let's run through a second check just to really cement this habit. Imagine a colleague on the desk hands you a script for a coin flip contract that pays out 10 pounds for heads and 4 pounds for tails.
Before you ever run their code, you hand calculate the expectation yourself. 50% of 10 is 5, 50% of 4 is 2, your total is $7. You now have your independent prediction.
This invariant discipline of predict, then run, then compare is what protects you when calculations get way too massive to verify in your head.
So, Section 5, Python you can actually run. Let's write that first script.
Open up a plain text editor and type exactly what you see here into a file named hello_quant.py. Let's break down the code line by line. The first line simply prints our label text to the screen. The second line tells the interpreter to mathematically calculate this expression, using the asterisk for multiplication, evaluating the parentheses first, adding those values together, and then printing the resulting number. You save that file in your editor, then you jump over to your terminal and command Python to run it.
Now ask yourself, what happens if the terminal spits out £1, 10 pence? Well, because you made an independent prediction of exactly £1.0, you know instantly, without a doubt, that there is a bug in the code. Maybe your colleague mistyped a probability as 0.55 instead of 0.50. Because you verified the math first, you catch that silent error before it trades with real money. You never ever blindly trust a plausible-looking output.
Section 6 and 7, connecting this back to the macro projects and covering the common mistakes you need to avoid.
Everything we do later scales up from this one working command. Mechanically speaking, whether you're pricing the gas swing engine, running a spread option risk tool, evaluating a storage model, or loading up a massive book of complex trades in the Chapter 99 Streamlit dashboard, it is exactly the same act you just performed. You're writing instructions in a file and running that .py file through the terminal. It's the same foundation.
But you've got to be on guard against these classic week 1 errors. We already talked about checking the Add Python to Path box on Windows. Another huge one is running your code in the wrong directory. Always make sure you've used the cd or change directory command to navigate to where your file is. If your terminal is looking in your Documents folder, but your script is sitting on your desktop, Python is just going to tell you the file doesn't exist. Oh, and critically, never write your code in Google Docs or Microsoft Word. They silently replace your normal straight quote marks with curly smart quotes, which will immediately corrupt your Python syntax and throw an error.
All right, Section 8, our recap and self-check. Let's consolidate the core lessons from today. Your lab consists of 3 distinct parts: the editor, which only saves the text, the terminal, which issues the command, and the Python engine, which actually executes the code. You can verify your setup right now by typing Python --version into your terminal. And above all, adhere to the golden rule of the trading desk. Always verify your code against a hand-calculated expectation before you trust it. With your terminal door now wide open to every single model in this 100-chapter course, you are fully ready for the real work. I'll see you in Chapter 6, where we leverage this exact environment to build variables, create loops, and actually calculate a multi-day P&L. But until then, I'm going to leave you with this thought. If a multi-million-dollar trading model spits out a number today, do you have the independent prediction to prove it's right, or are you just blindly trusting the machine?
Welcome to this explainer on Front Office Quant Foundations. I'm your instructor from Durga Analytics, and today we're going to take a really rigorous, engineering-focused look at the core Python building blocks used literally every single day on a live trading desk. We are going to treat this material exactly as it's applied in the real world of gas and power commodities. So let's just dive right in.
But real quick, before we get into the weeds, let's remember exactly where we are. This sits inside our massive 100-chapter curriculum, which spans 12 modules. We progress from basic front office quant fundamentals here in Module 1, all the way through commodity markets, forward curve construction, pricing, and those final capstone desk projects in Module 12. Today, we are specifically tackling Module 1, Chapter 6. This is where you get the exact syntax and the foundational logic that we are going to rely on for every single upcoming desk project. It's absolutely crucial.
So our agenda for today goes like this. First, course context and desk reality. Second, the 4 core blocks. Third, the math of telescoping P&L.
Fourth, Python execution and validation. Fifth, desk application and pitfalls. And finally, a recap and next steps. Okay, starting right off with Section 1, Course, Context, and Desk Reality. You know, as a quant, your absolute primary job is usually computing profit and loss over many, many days. To get there, we strictly follow a logical progression. We always move from understanding why a problem matters straight to the big picture. Then we build up the tools, understand the underlying math, execute the Python code, apply it to a real desk project, and finally recap. We literally build your foundation brick by brick. No skipping steps. And here is a bit of a reality check from the desk. If you ask a professional quant what tools they actually use the most day to day, the honest answer is almost never stochastic calculus. I know, right? The really complex pricing engines you'll build later on, things like Black 76 options or gas storage models, they look completely intimidating. But when you crack them open, they are ultimately just pristine, highly organized arrangements of 4 very humble foundational tools. You really don't need to be a computer scientist to be a quant, but you absolutely must master these primitives. Which brings us to Section 2, the 4 core blocks. These 4 fundamental tools have one shared job, which is building a robust P&L function. You've got a variable holding a single price, a list holding a sequence of prices, a loop iterating through them, and a function wrapping the whole shebang up. You capture the market inputs, step through them, compute your logic, and package it up so you can use it again and again. Let's quickly break them down, starting with the variable. Basically, think of a variable as a named box that just holds a value. You put the name on the left side of the equals sign and the value on the right, like price equals 30.0. This simply allows you to seamlessly reuse that specific value in your logic later, without ever having to hard code or type that number out again. Next up is the list. A list holds your sequence data inside square brackets, with everything separated by commas. Now listen, this is the crucial point, and you literally must burn this counting from 0 rule into your memory right now. You read items by their index, and the first item is always at index 0, meaning prices 0 is your first price. This trips up nearly every beginner, so lock that in immediately. Tool number 3 is the loop. The loop is your engine for iteration. It basically tells Python, hey, do this exact calculation for every single item in this list. So rather than manually writing out a daily change calculation for, say, 365 days of forward gas prices, a single loop just dynamically runs through each day completely automatically. It's a massive time saver. And the 4th block is the function. Functions are what prevent you from copy-pasting code on the desk. You define it once using the keyword def, you use inputs, which we call arguments, to pass your data in, and crucially, you use a return statement to hand the result back. If you ever find yourself copying and pasting a calculation, stop. That is a function waiting to be written. This discipline right here is the difference between a tangled, messy script and robust, professional software that a trading desk can actually trust in production. Now, while we are mainly focusing on those 4 core blocks, a dictionary is your essential 5th tool. Think of it as a labeled lookup using curly braces. Where a list asks, what is the 3rd item? A dictionary asks, what is the value named X? This perfectly handles market data. For instance, you might have a key named TTFU for the Dutch gas hub, pointing to a specific price value. In fact, a forward curve is essentially just a giant dictionary mapping future delivery dates to prices. Moving right along to Section 3, the math of telescoping P&L. Before we go and write the actual Python function, we need to understand the underlying math for calculating daily profits and losses over a multi-day period. Let's say you hold a fixed position of 100 units. The price goes from £30 up to £31 and then to £33. If we do the day-by-day math, day 1 is 100 times the £1 change, giving us plus 100. Day 2 is 100 times the £2 change, giving plus 200.
Total it up, and you have a 300-pound profit. Now, look at our shortcut formula. Position multiplied by the total price difference. 100 times the difference between 33 and 30 is exactly 300 pounds. They match perfectly.
So let's test this concept a bit harder. Imagine the price swings violently. You start at 30 pounds, it spikes up to 35 pounds, crashes all the way down to 28, and finishes at 33 pounds. Let's run the day-by-day math again. 100 times the change to 35 is plus 500. 100 times the crash to 28 is minus 700. 100 times the recovery to 33 is plus 500. Sum all those up, 500 minus 700 plus 500 perfectly equals a $300 profit. It's the exact same as our shortcut. This happens because the intermediate prices physically cancel each other out in what we mathematically call a telescoping effect. For a fixed position, the price actually took doesn't matter at all. Only the absolute first and absolute last prices do.
All right, Section 4, Python execution and validation.
Let's bring those 4 blocks together and build this out in Python. In our function, let's call it total P&L, we take in a position and a list of prices. We set up a running total variable starting right at 0. Then we write our loop, but pay close attention here. We loop starting at index 1, not day 0. Why? Well, because day 0 is the very first day. It literally has no yesterday to subtract. So we start at index 1, calculate today's price minus yesterday's price, multiply by the position, and then accumulate that new value straight into our running total.
Now, once your function actually returns a result, you must validate it against that telescoping shortcut we just talked about. But here is a massive engineering rule for you. Never, ever compare float variables directly using the double equal sign. Computer decimals carry microscopic rounding quirks. As an instructor at Durga Analytics, I see junior quants make this mistake constantly. Instead, you have to adopt the front office standard. You calculate the absolute difference between your loop result and your shortcut, and you check that it is less than 1e9. That's 1 times 10 to the negative 9th power. This tolerance check is what ensures robust mathematical validation without false failures.
Which brings us to Section 5, Desk Application and Pitfalls.
The exact function we just built is precisely what you are going to use in Project 4, the Trader Risk Dashboard. But you need to watch out for a few traps. The most common pitfalls include off-by-1 errors. Like we said, if you start your daily change loop at index 0, Python is going to try to read index -1 as yesterday, which will silently give you an entirely wrong set of data. Another huge trap is forgetting the return statement at the very end of your function block. If your function computes everything perfectly but hands back none, you just forgot to return the value. And finally, the disaster of copy-pasting your logic instead of properly calling and reusing your beautifully established function. Don't do it.
Finally, Section 6, Recap and Next Steps.
Let's do a quick self-check to make sure these concepts are totally locked in. Why do we use that tiny tolerance check instead of an exact double equals match? Remember, computer decimals carry microscopic rounding quirks that are deeply embedded in the hardware itself. 2 technically correct calculations can mathematically differ by 0.00000001. So comparing with a tiny tolerance ensures your automated desk validation doesn't just fail spuriously over a tiny hardware-level quirk. Let's test that map intuition one last time. You hold a fixed position. The price starts at 40 pounds, jumps up to 55 pounds, drops to 38 pounds, and ends exactly at 40 pounds. What is your total P&L per unit? It's 0, exactly 0. Since the start and end prices are completely identical, the fixed position nets nothing. This proves the telescoping concept perfectly. The chaotic path in between is totally irrelevant as long as the position stays fixed. With these 4 bricks, variables, lists, loops, and functions, completely mastered, you've got the foundation. Every single pricing engine in this course, and honestly, most of the ones on real trading desks, are built from exactly these pieces. You are now officially ready for Chapter 7, where we will bring in real-looking market data. But before we go, I want you to ask yourself this. If a simple fixed position causes all those intermediate prices to perfectly cancel out, what happens to your math when that position starts changing dynamically every single day? We are going to tackle that exact problem in our next explainer. See you there.
Hey everyone, and welcome back to this explainer. I'm your instructor from Durga Analytics, and today we're rolling up our sleeves and getting hands-on with Chapter 7 of the Front Office Quant curriculum, your first market calculation in Python. Now, if you've been following along with us, you know we've spent some time mastering the vocabulary and the raw tools of the energy trading desk. While today is where those tools actually earn their keep. We are going to take a week of realistic market prices and engineer the exact numbers a trader asks for at the end of every single day. Let's dive in.
Just to quickly ground us in the big picture here, our whole curriculum spans 100 cumulative chapters across 12 modules. It's designed to take you from the absolute basics straight through to advanced commodity derivatives pricing and system architecture. Right now, we're closing out Module 1, which covers Front Office Quant Foundations. And before we can tackle the really heavy stuff later on, like forward curve construction or complex gas structures, we absolutely have to solidify our core mathematical and engineering foundations today.
So here's our syllabus for today's explainer. Where we are today, why this calculation matters, load, compute, and summarize, the math behind returns and P&L, Python output and sanity check, and finally, common mistakes and next steps.
Okay, Section 1. Where we are today. Following the chapter's path.
Looking at our mental journey here, notice that we aren't just blindly jumping into code. That's a huge trap. Instead, we start with a business problem, then we map out the big picture architecture, do the actual math by hand, and only then do we translate that into Python. Finally, we'll connect it to the capstone project. Remember, as an engineer on a trading desk, you should always understand the math manually before you ever write a single loop.
Moving to Section 2. Why this calculation matters. The trader's dual view.
On a gas and power desk, a trader needs the answer to two very specific questions at the end of the day. How did the price move? And what money did I make? In other words, daily returns and total profit and loss, or P&L. Now, to build this out, our source text makes a absolutely critical architectural point, especially for the software engineers watching. We are doing this in plain Python. No pandas, no NumPy. Why? Well, because as the quote says, a hidden loop is a loop you can't debug. Writing the day-by-day calculation yourself first, with every single step visible, builds a robust mental model. When a pandas command inevitably gives you a weird output in production down the line, you'll know exactly which step to suspect.
All right. Section 3. Load, compute, and summarize. The universal data pipeline.
This diagram brilliantly illustrates our workflow. It's simply load, compute, and summarize. Honestly, whether you're building a quick little script, a risk report, a backtest, or a massive enterprise valuation dashboard, the underlying skeleton is identically shaped. It's the universal pipeline.
Let's break those 3 steps down a bit. First, you load the data, meaning you bring your daily power prices into the system. Second, you compute something per row, so calculating the returns and P&L for each specific day. And third, you summarize into headlines, aggregating that daily data into a total P&L, or maybe finding the best and worst single day. If you learn this shape on 10 prices right now, the only thing that changes when you hit 1,000,000 prices later is just the scale. The architecture stays the exact same.
Section 4. The math. Returns and P&L. Building from zero.
Okay, let's step up to the whiteboard and build up the daily math. Imagine we hold a position of positive 100 megawatt hours. Before we look at any actual numbers, let's intuitively grasp these two formulas. Daily return is just the proportional change. It's today's price minus yesterday's price, all divided by yesterday's starting price. Daily P&L, on the other hand, is the actual real-world money made or lost, your position multiplied by the absolute change in price. Let's walk through this manually, step by step. On day 1, our price is £30. No change yet, so no return and no P&L. Day 2, the price moves up to £31.50. Our return is 31.5 minus 30, which is 1.5, divided by our starting price of 30, giving us a nice 5% return. Our P&L is our 100 megawatt position times that £1.50 move, giving us a positive £150. Now look closely at day 3. The price moves from 31.5 to 33. That's another £1.50 jump. Our P&L is exactly the same, positive £150. But what about our return? It's 1.5 divided by the new, higher base of 31.5, which equals 4.76%.
So, this perfectly contrasts the trader's dual view. P&L cares about the absolute monetary move, right? A £1.50 jump on a 100-unit position makes you £150, period, end of story. But the return? That cares about the proportional move. A £1.50 jump represents a slightly smaller percentage gain if your starting price was already higher. You absolutely must hold both of these numbers in your head to understand market behavior.
And of course, in the real world, weeks have down days too. If on day 4 the price drops from £33 down to £32, the math handles it seamlessly. 32 minus 33 is negative 1. Divided by 33, that's a negative 3.03% return. And 100 times negative 1 is a negative £100 P&L. The mechanics are completely identical, only the sign flips. This is critical for our Python loop. We literally just let the negative numbers quietly cancel out the positives as we sum up the week's total.
Section 5. Python Output and Sanity Check. Trusting your code.
Now we transition from our manual whiteboard math to actually trusting our code in production. How do we know our Python loop actually worked and didn't drop a day? We use what the source calls a telescoping sanity check. Guys, this is an indispensable engineering standard. You never, ever trust a loop you haven't verified mathematically. Instead of summing up every single day's P&L, we take a mathematical shortcut. We simply multiply our total position by the difference between the very last price of the week and the very first price.
To put that into perspective, let's say our first price on Monday was £30 and our final price on Friday was £38.50. That is an £8.50 difference overall. Multiply that by our 100-unit position and we get £850. If the sum of your daily looped P&L does not perfectly match this £850, your loop is broken, period. This one simple line of code catches most loop bugs instantly.
And this brings us to a really exciting realization. This simple 3-block Python script, load, compute, summarize, with a built-in sanity check, is the literal skeleton of the capstone projects in this entire curriculum. When you build the real-time trader risk dashboard in Module 12 with a full web UI, you are going to see this exact same architecture hiding underneath hundreds of lines of code. It all starts here.
Finally, Section 6. Common mistakes and next steps. Avoiding the traps.
Before we wrap up, let's rapid fire through some common pitfalls engineers face when putting this calculation into production. The source highlights 4 classic traps. First, the dreaded off-by-1 error. If you load 10 days of prices, you only have 9 daily changes. There is no change on day 0. Second, summing percentage returns. Just don't do it. Adding daily percentage returns is a completely flawed approximation because proportional changes compound multiplicatively. They don't add linearly. Summing P&L in pounds, however, is exact. Third, skipping that telescoping sanity check we just talked about. And finally, dividing by the wrong day. A return is the change divided by yesterday's price, not today's. If you divide by today's price, you'll get a subtly wrong number that still looks totally plausible, which is exactly the kind of nightmare bug that survives all the way to production.
So, We've executed our first market calculation, we truly understand the dual view of returns in P&L, and we've verified our loops mathematically. But I want to leave you with this provocative thought. How exactly does this tiny load compute summarize script scale up across a massive portfolio of trades with complex user interfaces? Well, that is exactly what we will uncover in Chapter 8, where we'll see how these foundational building blocks create for real-world applications. Thanks so much for joining me on this Durga Analytics Explainer, and I will see you in the next one.
Welcome back to this Durga Analytics Explainer. I'm your instructor, and today we're hitting a massive milestone. We've officially reached Chapter 8 of our Front Office Quants course for commodities. Now, up to this point, we've been laying foundational gherks, right? Learning about the trading desk ecosystem, getting our market vocabulary straight, and locking down those Python fundamentals. But today, we're zooming way out. We are going to review the architect's blueprint for the exact production-grade applications you are going to build. And let me be clear, we aren't talking about toy scripts here. We are building a portfolio of 4 working apps that a real energy desk would immediately recognize and deploy.
Okay, let's dive into this. Think of today's agenda as our strict engineering design review for the entire system architecture. We'll start with the complete course roadmap, then move into the big picture system architecture, break down our 5 core production components, explore the unifying mathematical engine, lay out the workspace setup and dependencies, and finish up with a recap and next steps.
All right, kicking things off with Section 1, the complete course roadmap. This is our macro view, a grounding checkpoint before we move from our foundations into the actual markets themselves. Just to give you the exact view of our progression, this entire course is a massive, cumulative 100 chapters spanning 12 modules. Right now, we are wrapping up Module 1, Front Office Quant Foundations. Here in Chapter 8, we're placing the final cornerstone of this first module. It acts as the critical bridge to the rest of the course. From here, you'll tackle commodity markets in Module 2, learning how physical gas and power actually behave. Then Module 3 covers mathematical foundations like Monte Carlo methods. Module 4 gets into forward curve construction. Modules 5 and 6 tackle pricing. 7 and 8 handle risk and quant libraries. 9 through 11 cover programming and model risk, all leading up to your capstone desk projects in Module 12.
So why does this specific blueprint matter so much on a real trading desk? Well, it's simple. A disjointed script costs a desk money, but a fully integrated system makes money. We aren't writing isolated, throwaway code snippets. This whole course is designed as a massive engineering project, and knowing exactly which chapter lays which brick is what turns 100 isolated lessons into one powerful, cohesive enterprise system.
Moving right along to Section 2, the big picture system architecture. Let's talk about how those individual bricks become actual buildings.
And this brilliantly illustrates our whole engineering philosophy. At the very foundation, you have your individual chapter code, your loops, functions, and variables. Those are the bricks. Those stack up to build Component 0, which is a reusable foundation. Component 0 then feeds directly into projects 1, 2, and 3, which are our specialized pricing engines. Finally, every single one of those feeds into Project 4, the integrated capstone dashboard. It's a strict hierarchy showing exactly how software scales on a live, fast-paced trading desk.
Which brings us to Section 3, 5 core production components. We are now going to explicitly detail the expected inputs and outputs for every single component in our production pipeline.
First up is Component 0, the curve builder. If you've spent any time around commodities, you know that the forward curve, the set of prices for delivery on future dates, is everything. Every valuation needs a forward curve, making Component 0 the absolute bedrock of our entire system. It's a reusable library that ingests raw, real-world market quotes and outputs a functional curve object. Because raw quotes only give you benchmark dates, this object interpolates every single day in between, so your models have continuous arbitrage-free data. You can literally ask Python, curve.price, March 26, and it hands back 42.10 per megawatt hour. Without this piece, nothing else works.
Next is Project 1, the gas swing pricing engine. Now, what's the business problem here? A swing contract gives the holder the flexibility to take a variable amount of gas each day, completely at their discretion, but bounded by strict daily and annual limits. And these aren't just arbitrary numbers. These constraints represent actual physical pipeline capacities and take-or-pay clauses. So this engine values that flexibility. The output tells a trader, hey, this annual gas swing is worth 1.84 million pounds. And crucially, it gives them the exact optimal daily take strategy to actually realize that value.
Then we have Project 2, Power Spread Option Risk. This engine prices a spark spread option, which is the financial right to basically convert gas into power through a power plant. Gas is your input fuel, power is your output. This option's value relies heavily on the plant's heat rate or efficiency and the intricate correlation between gas and power prices. The output you get is twofold: the fair value, let's say 320K, and the exact risk sensitivities, or Greeks. You might see a delta of plus 0.62 to power and minus 0.55 to gas. Those specific risk metrics are absolutely essential because they dictate exactly how a trader needs to hedge their book.
Project 3 is our storage valuation model, where we optimize physical assets against market volatility. So, the crucial point here is understanding the contrast between intrinsic and extrinsic value. On one hand, we have intrinsic value, say 2.1 million pounds. That's the guaranteed profit you can lock in today from the known forward curve, simply by buying low in summer and selling high in winter. But on the other hand, we have extrinsic value, say 0.9 million pounds. That's the added optionality you get from retaining the flexibility to react as prices bounce around in the future. Sum those together and you get a 3.0 million pound storage valuation, all strictly bound by the physical injection and withdrawal rates of the storage cavern.
Finally, we reach our capstone, Project 4, the Trader Risk Dashboard. Built across modules 8 through 12, this Streamlit web app is the ultimate aggregator. It loads an entire trading book of all the structures we just talked about, builds the curves using component 0, prices every trade using projects 1, 2, and 3, and puts live position, P&L, and risk right on one screen. Why is this a game changer? Because in fast-moving energy markets, relying on stale risk data is incredibly dangerous. This app puts the entire desk's risk in front of you, updating live the second the curve changes.
All right, Section 4, the unifying mathematical engine. Let's shift gears and look at the core mathematical philosophy that actually drives every single one of those pricing engines. There is one mathematical thread running through this entire system. It all boils down to this fundamental equation: value equals the average outcome across all possible futures of making the best decisions allowed. At its heart, stochastic optimization is just this one intuitive principle, scaled up to handle heavy constraints and multiple commodities. And when we say all possible futures, we're literally talking about generating tens of thousands of Monte Carlo price paths in Python. It's like a giant what-if machine. Let's map this unified math directly to our projects. For the swing contract, you're calculating the average best daily take decisions over those price paths. For the spread option, it's the average best exercise decision over correlated gas and power paths. For storage, the average best inject and withdraw schedule over those same paths. And the dashboard just sums the values and risks of it all. So the exact same underlying logic effortlessly adapts to value incredibly different energy structures.
Okay, moving to Section 5, workspace setup and dependencies. Let's transition from theory to execution and outline our strict deployment roadmap.
Treat this as a real deployment pipeline review. Sequence absolutely matters in software engineering. First, we have to build component 0. Second, we can build projects 1, 2, and 3 in parallel-ish order because they're self-contained engines. They rely on component 0, but not on each other. And finally, step 3 is building project 4 to aggregate everything. This exact dependency chain is what dictates the structure of the rest of the course. Now, what's really interesting about this slide is the absolute reality of these software dependencies. You literally cannot value a swing contract,
a spread option, or storage without a forward curve underneath them. If you tried to build the dashboard first, it would just be an empty screen. If you built the pricing engines without component 0, they'd have no prices to evaluate. The sequence isn't just a suggestion, it's mandatory.
Wrapping things up with Section 6, Recap and Next Steps. Let's close out Module 1.
I want to speak directly to you as quant developers right now. Here are the operational hazards you absolutely must avoid. First, treating chapters as isolated lessons. They aren't. They are sequential bricks. Second, skipping the reusable component 0. If you build a weak curve, it weakens every single model downstream. And finally, deleting your workspace code between chapters. Code accumulates. Reusing your shared helpers file is non-negotiable. Deleting it between modules is a surefire way to force painful rebuilds.
Let me challenge your engineering mindset for a second before we conclude. If Project 4 aggregates projects 1 through 3, how exactly should its code reuse those earlier projects? Think back to our reuse, don't rewrite principle. Project 4 does not re-implement the math. It imports those swing, spread, and storage pricers as modular components, then just loops over the trading book. That right there is how real enterprise architecture scales.
And just like that, Module 1 is completely in the books. You now hold the complete map, you understand the desk, the tools, and the 4 powerful applications waiting at the journey's end. Next up is Chapter 9, What Makes a Commodity and Why Energy is Special, where we finally dive headfirst into the markets themselves. But before we go, I want you to ask yourself, when you finally boot up that fully integrated risk dashboard in Project 4, what kind of alpha, what kind of trading strategies will your underlying math engine actually uncover? Something to ponder. Thank you for joining this Durga Analytics Explainer, and I will see you all in Chapter 9.